Hi, welcome back to the breadboard. I've had a few people that are in the communities that I help support asking about driving stepper motors and things with an Arduino, whether it be or other microcontroller. And I decided to put together a tutorial to help people understand how steppers work. The project that I've picked to help demonstrate this is the Frameless Laser Harp. One of the members on the Element 14 community site was asking about how to convert this from the Unipolar Stepper Motor that had 6 wires, where the two sides of the coils were basically split in two, so like center tap. And in this case, the center taps, as you can see here, are connected to the plus voltage supply, and the ends of the coils are going to the outputs of a ULN2003 Darlington driver. And what we wanted to convert it to was to use a bipolar stepper motor like this one from SparkFun. In fact, the actual user who was asking the questions is actually using this very stepper motor. So we wanted to be able to convert the program and convert the design to be able to use this. So the first thing that we had to do, of course, is pick a stepper motor driver or something that could be driving this, but keep it very simple and easy to implement without incurring a lot of costs. So what we did was we selected a Texas Instrument 754410. What this is a quad half H bridge driver, which means that you can actually configure it to completely drive a stepper motor if you want. And if I just scroll down to the actual, like a block diagram of this, you'll see what I was meaning. So this is the output stage. So you have your plus supply, say 12 volts as an example, coming in. It'll go through the transistor when when the top one's turned on, out through the output to the stepper motor coil, and then the one of the other half bridges will have the lower half turned on, which would then take the other side of the coil to ground, thereby energizing it. And then when you wanted to flip things around, you basically, change different combinations of these output transistors to suit what you need. And if we go down a little bit further, we'll see a basic connection diagram here. So what this is, this just has two inputs, control A and control B. They go into the steppers, and you see there's an inverter here that is making sure that the coil, whether it be coil 1 or coil 2, is always turned on. It's either being driven through this way or it's being driven through this way, and that all depends on which way control A goes, whether it's high or low. And the same thing for the other coil. We'll call this coil A and coil B. Same thing applies there. It's either driven from the top to the bottom or the bottom to the top based on control B. Now, in the circuit that we're using, we're actually not going to have these inverters here. They're not necessary. We're going to use an Arduino Uno, and we're going to drive pins 2, 7, 10, and 15 directly from the logic outputs of the Arduino Uno. And in the previous Design Spark Frameless Harp, that is pretty much what they did, but using a ULN2003. So if I go back to this project and show you here, you can see you've got the Arduino Uno, you've got a ULN2003, you've got 4 outputs, and we're going to use the exact same 4 outputs. And then you've got the 4 coils of the stepper motor, the Unipolar Stepper Motor. Each one is going to be getting grounded depending on the step position. But because the person that was asking the questions had a bipolar stepper motor, there was no common, and it didn't have the 6 coils. In fact, if I just bring across another picture for a second, this is, not sure what happened there to that. There we go. You can see here, this is the bipolar stepper motor right here. Sorry, unipolar stepper motor right here. So you've got one coil with a center tap, and you've got the other coil with a center tap. And in this circuit down here, the center taps, the commons, have both been connected to a plus supply. And then it's these 4, this one, this one, this one, and this one, that are being grounded in sequence to drive the stepper motor to make it rotate. The coil that we have, though, is not like that, and it's actually more like this. So you got one coil in one direction, one in the other. There is no center tap. So there is a different way of driving this from the unipolar one. You can actually drive them in the same way if you've got a more sophisticated drive logic, but I'm going to show you the differences and how we're going to modify the code to do this. So let me just get this frameless harp out of the way. So this one is the Unipolar Stepper Motor, and I've expanded it out. And what I'm showing you here is this is the coil. Now the internals of the stepper motor is a lot more complex than this. This is just a simplified view. And basically what happens is you'll power this one up, this coil, the top one, and you'll energize, and then the stator in the motor, it's magnetic, will align itself with the poles of the coil while it's being energized. And then what you will do is, instead of the pink one being energized, you'll now energize the orange, and all the other ones will be turned off. So the stator of this motor will move to now align itself with the new pole of the next coil that's energized. Then we turn off the orange, we turn on the yellow, then we turn off the yellow, and we turn on the blue. And what happens is, or is that black? Anyway, that one. The motor would then slowly rotate. So what you have here is, I've called this A naught, B, and B naught. So this would be A naught, B naught on here. So you start off with B naught energized and everything else off. So this coil here would be turned on. And then you start sequencing through them. So coil A, then B, then C, then D, then back to A, B, C, D. And then if you continue this sequence, the motor would basically continuously rotate. This short sequence here, based on a 7.5 degrees per step stepper motor, would have rotated around about 60 degrees, or on the stepper motor. And then the second half that I've got here is actually just doing the reverse, and what it'll do is it'll make the motor turn backwards. So you're only energizing one coil at a time. And this is one easy way and very simple way of energizing a unipolar stepper motor coil. And that's fine, and that will work in the example that was presented in the instructables. So what do you do if you have a bipolar stepper motor that doesn't have those center tap coils? So we go back to this diagram now. So what we have here is we have the same A naught, B naught, but the difference now is, instead of having the supply being driven into the middle of the coil and you're simply grounding either this side or this side, and the same would go for this one, we're actually supplying power into one end and grounding the other, or we're supplying power in this end and grounding this one, and the same thing would go for this coil. And what you're doing is you're basically reversing the magnetic field on that coil as you go around the steps. Now, in order to get a full rotation, you would have something like this. So you start off with, say, A energized, so you'd be flowing from here through to here, and you would have B energized, where you say flowing from here to here, and that would align the stator of the motor in a particular fashion. And then what you need to do is you need to basically rotate the magnetic fields of the coils, and the stator will follow it because it's permanently magnetized, the core of the motor. It will follow that magnetic rotation, and you always have a phased approach to the way that you energize these coils. And I'm keeping this stepping simple right now. I'm not going to go into micro stepping or even half stepping or anything like that. This is just full stepping, rotating that motor. So as you can see here, you have A on, then you take A off, and then you bring, but B is stayed on for the full cycle. Then you take B off, and it stays off for 2 cycles. And you can see here how the red is where you're applying positive, and the black is where it's grounded. And these are the 4 coils. So I know I haven't labeled them quite right here, but think of it as being A naught, B naught. And this would rotate. Now you can see this pattern here is very different from what was being presented in the first diagram for the unipolar motor, which is this one here. You can see the differences here. The 754410 quadruple half H driver. So we're going to have it configured as a full bridge, pretty much the way that this diagram is, but without these inverters. We're actually going to have control A, control B, control C, control D coming in. So this is going to be pin 8, 9, 10, and 11 of the Arduino Uno outputs. All right, so here's the original code that the Arduino had for the laser harp. And at the beginning here, you've got defining the motor pin. So you've got pin A, not A. I've just used upper and lowercase a, so upper and lowercase b for the two coils. So 8 and 9 is one coil, 10 and 11 is the other coil. I've done a little bit of renaming on some things here, but I haven't changed the code yet from what was being used to drive the laser harp as defined in instructables using a unipolar transistor. So I'm just going to scroll down and bypass some of the setup and things like that at the moment. I will stop and mention a couple of things here to help people understand what's going on. So first of all, this is outputting to a MIDI port for things. So this little bit here, note on off, is actually outputting the command, the pitch, the velocity for a MIDI instrument that might be connected to the laser harp. The loop here, well, where's the setup? The setup must be further down. Nope, setup's right here. So setup, we're just setting the 4 outputs for the stepper motor controller. There's also a laser pin, which we're turning on a small low-powered LED laser, so that and then there's a sensor that you would use for detecting whether the laser harp is the beam is being broken, and you can detect the reflection. That's further down, and it's on one of the analog inputs. So, and then you've got just a simple status LED on pin 13 just to say whether it detected the beam or not. And then the serial begin 31250. That's an odd baud rate, but that's because this is for MIDI. It's not talking to another computer or anything. So let's just scroll down to the loop. So what this loop does basically is, so it turns on the laser, waits a little bit, reads the sensor. If the sensor is detected, it sends out a note. And if the sensor is not detected, it turns that note off. So if you're taking your hand out of the beam as an example, it'll turn it off. If the beam's broken, A gets reset to 0, which is fine. We then turn the laser beam off, and then here is where we move the stepper motor to its next position. So you can see here, this is based on one coil being energized at a time, and you'll see that as we go on. So this is going to be using this pattern. So right now, this has got pin A high, A naught is low, B is low, C is low. So this one's high, low, low, low. And this is the pattern here that's going to get reflected in this code as we go through. So then we delay a little bit of a delay for the motor. We turn the laser on. We see if the sensor has been detected. If it has, we play another note, and if it hasn't been detected, we turn the note off, and then we turn the laser off, and then we do it all over again. Only this time we're energizing the next coil. And we keep repeating this 8 times. So you can see there's a lot of code here. And then what we do is we actually then start reversing it. So we go back to the diagram here. This is assuming the starting position here. So we go 1, 2, 3, 4. 5, 6, 7, 8. There's 8 steps, but there's 9 notes because it assumes that note 1 is the one we start with. So it basically sweeps the stepper to the right or clockwise, just depending on how it's wired up. But anyway, let's assume clockwise. And then it's going to reverse it and sweep it back anti-clockwise back to the starting position. So basically what's going to happen with this loop is it's going to keep flip-flopping the stepper motor about 60 degrees in clockwise, 60 degrees anti-clockwise, clockwise, anti-clockwise, turning the laser beam on and off for each step. So as we go down here, you can see we're now starting going 8, 7, 6. Now, one of the things I'm noticing here for the status is it's got the D++ for note 4, note 3 is C, so they've assigned a variable for each note. So if the sensor is detected and the particular note is not already on, so if this is greater than 0, then the note's going to be already on. It's going to continue, and it's not going to redo this. We know it's already playing, so we don't need to send this out again. So you don't get any additional glitches or anything like that. The status is already on, so we save a little bit of time by not executing this. That's what those are for. And then we come down to the end here, and then the very last one takes us back to position 1, and we go back to the top, and we keep repeating this. So the first thing obviously that's wrong here is that the sequencing of the stepper motor coils is wrong. This is the code that the member is asking on the forums, and you can see here that here's the different tones for the note generation. Notes being played all the time is pretty much always the same thing. There's only one thing that's actually changing if I just find one. So you've got the note here. You've got the, where was it? Let's just go look at the note thing again a second. So you've got the command, the pitch, and the velocity. So the pitch is the second, the command is the first one, second one is the pitch, third one is the velocity, which I think might be volume or something like that, but anyway. So if you look at one of the note playing commands, we've got command is 90, that's the pitch, and then this one's the velocity. And I think in all cases the command is always 90. And when we're turning it off, the velocity is 0. So for each one. So this could definitely be simplified as far as note on and off. We could put this into a separate routine, like a subroutine of its own. And the rotation of the stepper motor here, it's all being done manually, but the Arduino has available to it a complete stepper motor library. So what we're gonna do is we're gonna use the stepper motor library because it already implements the correct cycle for the stepper motors, which is this one. And by simply saying step 1, step 2, step 3, or whatever you want to do, it will automatically rotate the motor that number of steps. And if you say step -1 or 2 or 3 or 4, it will rotate it in the opposite direction. So we can drastically simplify this program. So let me just go grab the libraries. They're the standard Arduino ones, actually. So if I just go in here and show you in examples for standard install, here's one for stepper. And we'll look at one step at a time right here. All right, let's just bring this into view. This is the complete sketch. All it does is drive a stepper motor. You can see we're using the exact same pin. So 8 and 9 is coil A, 10 and 11 is coil B. And to use it, we include the stepper library. And there's nothing in setup for this because it's all handled inside the stepper library function initialization. And then all you do is here, so you can see is step 1, and it just moves it around one position. We don't need these print lines, and the step count is just keeping count, so it's sending out of the serial port what the steps are and everything. So let's start going back to the code and start modifying it for this new, to use the stepper library. So of course the first thing we need to do is include the library. So let's just add this at the top here, leave that down. We've got the pins defined, everything else can stay the same. This is all the same for now. So the first thing we're going to do is simplify the stepper routines. All right. So because we're using the stepper library in setup, we don't have to do anything special. All right. But outside of setup, we need to initialize the stepper. Actually, we do need to know the steps for resolution. So let's just take this piece of code and we'll stick that in here. Now, the stepper motor we've got is a 7.5 degrees per step stepper motor. So I happen to know that the steps per resolution is 48. If you simply divide 360 by 7.5, you'll get 48. So we'll change that to say 48 steps per revolution of this stepper motor. All right, the next thing we need to do is we need to initialize an instance of the driver. So we'll just drop that in there. And what this does is creates an object called myStepper that we can use to actually control the stepper motor. We tell it the number of steps per revolution, which is up here, and we tell it the pin numbers we're using. Now I'm just going to modify this to use the definitions we've got. B0. Now you should have the pins declared before the use of it, so we'll just switch that around. So we've got the pins and then we've got the initialization. So now what we're going to do is we're going to use myStepper and we're going to say +1 or -1 as we go here. Now what I'm also going to do is add another variable which I'm going to call it int step size equals 1. And what this is going to be used is so that just to start with, we're going to say only do one step, but if anybody using the code wants to make it step 2 for each increment, then they can just change this one variable instead of finding all the places in the code and have to change it everywhere. You can just change this one thing. So we're going to use step size when we call for stepper motor. So let's go down here. This can now go away because it's taken care of by the stepper motor driver, so that's gone. Pin mode, laser pin. This one's for the status LED, and that's for the MIDI port, so that's all fine now. And we've got, okay, so no on, this stays the same. So let's have a look at this loop section. So what we have here is we turn in the laser on. So we're assuming the motor's already energized and at its starting position. So that's one of the flaws of this program, is that when you turn this off, it could have actually stopped the motor at any position. So there's no guarantees that it's actually going to start in the right place. So that's something that would probably have to add to this program at some point. By maybe having a little sensor to know where the position of the motor is currently. Anyway, that aside, we're just going to get this working for now with the bipolar stepper motor. So we turn the laser on, we wait a laser time, we read the analog value from the sensor, and if it is sensed, we play a note, otherwise we don't play a note. So we're going to leave that alone for now. We're going to come back to all of that stuff afterwards. And then at the end, we turn the laser off again. Now here's our step. These 4 calls are all the same thing. So we can now replace this with a single step command. I'm just going to pull things right from this other code as I do this. So we're going to replace all of that with a step 1. And that's all you need to do. So let's just put a comment in here. So now we turn the laser pin high again and we step again. So this is another one where we are moving it the next position. So we can replace this with that. So we just reduce that one. All right, so we get to 9, and then what happens now is it starts to actually go into reverse. So this one is going to have to be a -1. It's exactly the same thing, but it's a negative step. So let's just put this in here, and we'll change this to be -1. So we'll just change the comment to go with it, and we'll copy this. All right, let's go down here. So this is another -1. Finally, we're back to the starting position again, and it loops around. So you can see now that this is a lot shorter than it was. Now, the problem with this is it's still quite long, and it's repeating a lot of the same thing. So we need to try and simplify this even more. I mean, right now this will work. It will drive the stepper motor correctly, and it's going to go forward and backwards, and everything's going to be happy, aside from that bit that it doesn't exactly know where it's going to be starting from. The next thing we need to do is look at how we can actually simplify this. So the first thing we can probably simplify is turning the note on and off. This whole thing with the notes, if it's detected, blah, 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 if it's not detected, etc. We can probably put into a function that will do this. The 90 and the 7F and the 90 and the 00 on these 2 different calls here, they never changed. Anything that actually changes here is the note itself. And we can pass that in. We can index that with a number anyway, because it's note 0, 1, 2, 3, 4, 5, 6, 7, 8. So we're going to look at simplifying this a little bit. So the first thing to do is probably to put the notes up here into an array of notes. So right now this is note 9, 8, 7, 6, 5, 4, 3, 2, 1. And what we're going to do is we'll create a int array notes instead. All right, so now we got the same thing here. It's note 9, 8, 7, 6, 5, 4, 3, 2, 1. Unfortunately, that's not the way I wanted it, so I actually want these to be reversed. All right, so now we can get rid of these. You potentially could get more than one note playing at a time, so what I want is this one as well. I also want to be an array of ints for the counters, so it's going to be the same for each note. This actually aligns with this. So we're just I'm gonna create this, and we can index this as a simple array. But what it does is it allows us to actually have a function that takes a single parameter, which is which note do I want to play, and then it can take the tone from this array, and it can set the status by that increment into this array. Now I could make this booleans as well, but I'm going to keep it as close as I can to what was in here. So now we can get rid of that. The one thing we noted before was that the command is always 90, and it's either on or it's off. Okay, so I just create a variable called velocity on for taking this velocity in, and we know that it is 07F is what's used everywhere when we turn the velocity on, and we'll make another one for velocity off, just so when we get the turn the note off coming in, and that is just 00, and the command I think is still 90 even when we're turning it off. Yeah, it's always 90. See, there's on and off. So I'm going to separate this to a note on and a note off just to make life easier, because we're going to be reading the sensor, and then if it's detecting it we want to say note on. If it's not, we want to just simply say note off. So what we're going to do here is we're going to say note on pitch index, and we'll get rid of the on off for now. We'll use that somewhere else. So it's just going to take the one parameter. So we've got this, we don't need, we can take these, let's just put these out of the way. We'll put them up top here with the other bits and pieces and stick them in here. All right, just so they're out the way. All right, so we say turn the note on. So we write the command, write the note pitch, and we want this if it's, no, we want this now. So okay, let's just change this because we're not going to turn it off, so we don't want to always have the command. So we're going to move this outside here just so that we don't even do the command. So if the note is already on, we don't need that anymore. So if the note is already on, if the note's not on yet, write the command, write the index, just rearrange this a little bit. Write the velocity, increment it, turn the LED on, and that is it. So what we'll do is we'll finish that function. Have I got this right? So if that, I got a bracket missing here, just put that in. All right, let's just tidy this up a little bit. Hold on. Auto format, Control T, there we go. Makes it a little prettier. So note on, if the note is already on, don't do anything. So if the note's not already on, write the command, give it the pitch, give it the velocity, increment it so we know it's now on, so it won't do this the next time through. Turn on the LED, and we're done for that. So now let's do note off just as a separate function. This is, I know you could probably combine this, but this probably makes it just a little bit easier, and you'll see why. So let's just call this one off, and we got the pitch. So if note stay, well, we don't care about that now because we're just going to turn off whatever it is. If it's already off, I'm sure it won't care. So we're just going to write command pitch off, note pitch index equals 0, and turn off the LED. And we now know it's 0, so if we get it on again, it's going to turn on. Get rid of the extra bracket. So there's our note off, there's our note on, there's our note off. So we can get rid of that because it's no longer required. Now, what the other bit I was going to pull out of here, which is also repeating, is actually detecting the laser. Let's create an empty function for it. All right, so there's a function we're going to use for sensing the laser. So we want to say if analog input is greater than sensor. We don't need that because we're doing that in the other one. So we just want that. So if the analog input is greater than sensor value, we're going to do some kind of work here. I keep forgetting it auto-fills that. So we want to, the digital write high is already being done. The note is already being done. That's already been done. So if here's the other end, if it's less than sensor, in the else if. So let's just bring that in. So here's the first one, here's the second one. So all right, so if analog reads greater than sense, that means we want a note on, and we've got the index coming in. So we want to call note on and just simply pass it the index. And so this is now very, very simple. We just read the analog, and if it's detecting something, we turn it on. And if we're not detecting, if it's no longer detecting anything, we turn it off. We don't care what it is. It's just the index is from a loop now. So now here, we can even do this actually. Sense laser. So if we want to sense the laser, we'll turn on the laser, delay. So we'll take that out. So sense laser. So we go in here, turn on the laser. Delay the laser. If the laser is detected, that's that piece, and we're calling note on and off, that's that. And if it's less than sensor, turn off. We got that. So then we're just going to add to this, turn off the laser. So we'll take that out because that's also, we've done it all. So we turn on the laser, delay, turn off the laser, and we turn it off. I'm taking this the long way just so that you understand what I'm doing, if you remember that. So in the loop, we're going to say now, because all of this is taken care of here, we're just going to say sense laser 0, index 0, yes. 0 equals note 1. Remember, the array is a 0 index, so all right, so we're in position 0, so sense laser 0, my stepper plus 1. Sorry, increment, rotate the stepper motor, delay the motor. We've got that's already taken care of, so we don't need that. Now the next one, so we want, basically we're rotating again, only this time it's note 2. Okay, so actually this is moving to note 2, so let's just put a separate here. We'll just take that and we'll say here sense laser, and we want to do it for note 1. 1 equals note 2. All right, and that is all of this. All right, because we've also got the step here and the laser higher. Sorry, that's the end of it there. So all of that is now done with that. Now we want this again for the next one. So we're going to step and do note 3. Okay, so I've cleaned this up a bit. So what have we got? Include stepper.h, which brings in the library. We've got our standard motor pin definitions for a bipolar stepper motor using pins 8, 9, 10, and 11. We initialize a stepper object using the stepper library, giving it the pins and the steps per resolution, which in our case, given a 7.5 degrees per step stepper motor, is 48 steps. That's done with initializing the stepper library. The parameters we've got are the same. We've changed things to use a notes array instead of individually declared notes. Note 1, 2, 3, 4, 5, 6, 7, 8, representing note 1 through 9. The note state, instead of being A through H or whatever it was, is now an array that matches the one above. Preset all the variables to 0. We've then just declared the commands up here because we're going to reuse them. So we've got command for the MIDI of 90 to turn a note on. We've got velocity on of 7H and velocity off is 0, 0. Sorry, 7F, not 7H. In the setup, all we now need to do is to declare the laser pin with an output and the LED pin for the status as an output, and then we just begin the serial port for communicating with the MIDI interface. In the loop now, these are drastically simplified. Now I've moved sense 0 because we assumed that default starting position was at the beginning of the stepper, but there was no step to it, so who knows really where it is. And you see now that each of these is almost identical, so I've simplified it by just moving the sense 0 to the very end, because really technically it was I haven't moved its position, it's just in a slightly different place in the loop. So we increment to our first position, we delay. we then simply, and I'm not even sure if this is actually required now because the stepper motor controller software will probably take care of that. So we sense laser index 1, we move index note 2, we move note 3, we move note 4, we move note 5, 6, 7, 8, 9. When we get to 9, then we start coming back down again. You notice now from here, these are all plus indexes on the step. Now we're minus indexing, so we're going to reverse the steps. And we do the exact same thing. We got 7, 8, 7, 6, 5, 4, 3, 2, note 1, note 0. And there's our note 0. And then we go back up to the top again, which means we basically loop round. I've taken the functions and I've just put them down the bottom, which is more of the correct convention. So if we when we call the sense laser, which is this one, let me just move that up to in the order that we're going to be using them. I'll just put it in here. So in the sense laser, we give it the index. So it's either 0 through 8. So here's the index. We turn the laser on. We wait the laser delay time. If we read the sensor, we turn on the note. If we don't read the sensor, we turn that note off. Because there could be more than one sensor on at the same time, if you're using a MIDI synth or something. Then if we need to turn the note on, we come in here. We set the note. We check the note status to see if it's already on. If it is already on, we skip this. If it isn't already on, because the index is 0, which means it's not already on, then we send the command, the note index, and the velocity on command. That sends out the MIDI port to turn it on. And then we increment it to let us know and remember that it is on. And we turn the status LED on. If when we detect the sense laser, we detect that there is no laser for that index anymore, we call note off. And for the note off, we do serial command right, turn everything off. So in this case, the only difference between this one and this one is this one uses velocity off, this one uses velocity on. Now I think it might be worth, if this is already 0, we know it's off. So it might be worth doing the same thing here. So I'm going to just take this little bit and I'm going to wrap the off with the same kind of function. Only difference being it's going to say if it's greater than 0, in other words, if it's on, because if it's already off, why do this? Apply the same logic to this. So if the note pitch index is greater than 0, so if the sensor does not get a signal and the note is playing. All right, so now so basically we know we didn't get a signal. We're telling it to turn the note off. If the note is already playing because the index is greater than 0, then we send the command, we turn it off, and we set the index to the counter in there to 0, so we don't do this again. We set the status light to off for that note. Now, the one thing I see here with this status light is that if you've got more than one and then you take it away, the status light is going to go off. It's not going to leave it on for any particular note. So you're not really going to know which note, that's not going to work very well unless you're playing one note at a time. And that's probably okay, but it could do with probably fixing a little bit. Anyway, so as you can see, this is drastically simpler now. But we can actually make it even simpler. Now, I'm not going to take you through all of this on how to make this simpler. I'm going to save this exactly as it is and post it, and then I'm going to just simplify it. And what I'm going to do is basically have a loop for the first one counting up and a loop for the second one counting down, and it's just going to do both loops up and down and make life easy for itself. So I'm just going to do that modification. I'll quickly show you it, and then that'll be it. Okay, so done a final cleanup. I'll quickly take you through it. Declarations at the top, pretty much the same. Nothing's changed until we get to here. I've added an extra variable called array size, and it's size of the notes array divided by the size of one of the elements, because the size of notes will give me the number of bytes that it takes up, but I'm using integers, which typically are 16 bits. So rather than worry about exactly what type I have in here, I'm just doing size of one of the array items. So that'll divide it and give me the correct value here based on the size of this. So it should return 9. That's all I've done there. Now, nothing in the setup has changed. Now, in the loop now, you'll see this is dramatically smaller. And what we have is basically two loops. One that counts up, which is int counter equals 0, as long as the counter is less than the array size, because remember, it's index 0 to 8, not 1 to 9. So that takes care of that. And then we increment. And then each time we increment through, the stepper gets positive indexed, we delay, and then we sense the laser using the counter. So that indexes through the notes and allows us to control that. Once we've done that, we then index back down again. So we go from counter equals array size -1. We actually want to go from 8 to 0 this time, not 9. So this was subtracting 1. Remember here we did less than 1. Less than the array size, which actually meant we're comparing it up to 8. Here we're starting with 8 and we're going down to 0 and we're doing decrements instead. We increment the stepper negatively, which means it goes the opposite direction, same delay and the same sense laser with the counter. So what this should do is clockwise 9, anti-clockwise 9, and it should flip-flop between the two. Well, it's actually 8 and 8, but anyway. The sense laser has not changed, the notes on has not changed, and the notes off has not changed. But now, as you can see, this is massively smaller now than what we had before. So I will save this and post it. I actually don't have a MIDI controller to test. It compiles okay, as you can see there. If I just hit the compile right now. So theoretically, with all things being equal, this should now allow you to drive the stepper motor. What I will do is actually put the Arduino onto an oscilloscope and see if I can just capture the step outputs going and rotating through, and that'll show us whether it's actually behaving there, and the laser output should be toggling on and off as well. But I won't be able to detect anything because I don't have a laser pointer or a LDR to hand at the moment to be able to test the rest of it. So we will see how that goes. Okay, so I just uploaded the code into a Arduino and ran it. So I captured the traces on my oscilloscope using my Tektronix MDO3000, and here is the first trace. So the trigger point is right here when it started. So you can see here, first of all, this first trace is showing the 4 stepper motor outputs. And you can clearly see here that the phased approach, you see here's the A naught. So these two are just completely inverted from each other all the time. And then the B and B naught are completely inverted from each other as well. And you can see that the B is half a step behind the A's. All right, which is exactly what I was describing earlier in the video as to what it should be doing. So you can see here that the stepper motor driver utility is working just fine. Now there's a little funny thing here, and I'll explain what that is later. So this is the first picture that I took, and I think the next few are the same. Okay, here's the next one. So what it did was, now that I've already shown you that the the A and A naught are exact opposites, what I've got now is this is A and this is B. So this is coil 1, this is coil 2. And when this is high, it's energized in one direction. When it's low, it's energized in the other. Same for B. When it's high, it's energized in one direction. When it's low, it's energized in the other. So I don't need to show you all 4 signals anymore. And what I've done to this is I've added output 7, which is the laser on-off signal. And you can see here that right away when we start off, it goes to our first position and it turns the laser on, and then it does the sensing if you look at the code, and then it turns the laser off. It then does a step to the next position, waits a very short delay, and then it does a laser on, do the sensing, laser off, step again, laser on, off, step, laser on, off, step. Now here's that funny little kink we saw before, but it's actually not a kink. It's not, sorry, it is a kink, but it's not really funny. It's actually quite explainable. And if you count the number of pulses, remember we go up 8, so we step up in one direction 8 times and we step back in the other direction 8 times for a total of 9 positions representing 9 notes. Now if you count the laser on positions representing each note, you've got 1, 2, 3, 4, 5, 6, 7, 8. All right. Now, sorry, 9. Not the first one. It's from here 1, 2, 3, 4, 5, 6, 7, 8. No, sorry, that's the 9th one here. Yeah, So it starts off here, and so we've got 1, 2, 3, 4, 5, 6, 7, 8 steps. But at the 8th step, we actually reverse direction. So we actually go back this way. So that's why this is not twice as long as it would normally be. So then if we count that again, 1, 2, 3, 4, 5, 6, 7, 8. And there's the next one going back the other way, right? 1, 2, 3, 4, 5, 7, 8. 1, 2. So it keeps flip-flopping back and throw. And each time it does a step, it turns the laser on, does a read of the sense line, turns it back off again, moves to the next one after moving the stepper, does another read, etc. So here's the stepper controls going out, exactly as we expected. And here are the read lines going out. So that pretty much confirms as much as I can. That's the code been modified, extremely simplified into a number of little functions and a couple of loops. So it's much, much easier to maintain and work with. And basically, yeah, that's pretty much it. I wasn't checking the, I obviously don't have a laser connected, so I can't check the MIDI part of it where it outputs to the serial port, but I can only assume that that will probably work. I've got no idea. But the main thing and the main objective of this was to get the actual stepper stuff working. I think that there's been a lot of to and froing on the forums about how exactly this code should be modified. So I figured that, you know what, there's enough people asking about how to drive stepper motors with an Arduino and things anyway, that I might as well just put this quick video, well, over an hour, but nevertheless, together to show how to do it. Anybody else want to build this? Just look up Frameless Laser Harp. You'll find instructables, and if you look on the, I think, Element 14 website, there's also the member that was asking the questions there. But whether it's RS, components, Hackster.io, or wherever, this little piece of conversion should be able to help anybody, and the final code there should work quite fine. Obviously, where it has the note on-off piece, that could be adapted to use the Arduino for playing the notes or any other kind of tone generator or MIDI sequencer or something that you would want. Now, if you use the Arduino to play the notes, though, do be aware that it may interfere with the timing a little bit. This right now here is 20 milliseconds per division, so you will probably, let me see, 20 milliseconds. I haven't set a speed or anything, so that's 20 milliseconds here. So it's doing a whole cycle in 20, 40, 60 milliseconds. So yeah, it's doing several cycles a second. So you may not see it flickering, but it's probably fast enough. But as I say, I think you can probably take the delay statements out. Maybe I'll do another quick scan. I'll upload it without those delay statements and just grab the screenshot for that as well, and you'll be able to see how much faster it goes. So one final tweak to the parameters. What I did was I added a revolutions per minute for an RPM setting for the stepper motor, and I've set it to 300. And if you divide 300 by 60, it gives you 5 revolutions per second. So this is RPM. And then if you take the 5 revolutions per second and you, with 48 steps per second, sorry, 48 steps per revolution, you're doing 5 revolutions a second, that gives you 240 steps per second. And as soon as we're using 9 steps per scan, that gives us about 25 scans per second in the system. And here's a trace on the oscilloscope that I just did. Let me just make that a little bigger so you can see it easier. There we go. So you can see here, this is the start, the trigger point here. So we've got 1, 2, 3, 4, 5, 6, 7, 8. 8 going up, sorry, 1, 2, 3, 4, 5, 6, 7, 8, 9 going up, which is correct. And there's the little short one where it reverses direction. So then we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 in the other direction. And there's the other short one where we reverse direction again and start going back clockwise again. So you've got clockwise for 9, anti-clockwise for 9, clockwise for 9, etc. And it just keeps on doing that. And you can see here quite clearly now that this actually, now that I've set the parameter, matches the RPM. So if you wanted to scan a little faster, and your mirror is going to make sure, you know, your mirror is going to stick to your stepper okay, then you could increase that RPM up from that. Or if you wanted to scan a little slower, then you could decrease it by just changing that one parameter. Anyway, that's everything done. So that'll be it. If you have any questions, post in YouTube or on the relevant forums where you're reading this. Hope you enjoy.